So remember we were discussing minimum spanning trees previously, and we talked about one algorithm to produce a minimal spanning tree. We talked about Kruskal's algorithm. So now we're going to talk about a different algorithm that'll produce a minimum spanning tree. This is going to be called, so I'll just call it Prim's algorithm. So much like the last algorithm, I'm going to start by going over what is the algorithm, and then we're going to apply it. So you input in to this algorithm a graph G, which has to be, remember, a connected weighted graph with n vertices, where n is some positive integer. And then here's how the algorithm is going to work. It's going to build our minimum spanning tree. It's going to build a subgraph T of G. And you got to start with a vertex, with any vertex V of G, and you're going to start adding in edges. One by one. To an as yet unconnected vertex of G. And each time you're going to choose an edge of least weight. So it kind of works similar to the last algorithm. You're looking at least weight that's adjacent to a vertex of T. So this is the idea behind it. That's what you're doing. Now here's the procedure. So one, you're going to pick a vertex V of G, and you're going to let T be the graph with one vertex V and no edges. So this is a little bit different than our last algorithm. So you're going to start with a vertex, and you're going to let V be the set of all vertices of your graph except this initial one, except V. And then here we have a for loop. So for I equals 1 to n minus 1, you're going to do this procedure. So I'll just label in 3A. You're going to find an edge E such that two things has to happen. So one, E connects T to one of the vertices in V. So this edge has to have one vertex in T and one vertex not in T. And two, E has to be the least weight of all edges connecting T to a vertex in V. in V. And we're going to let W be the endpoint of your edge that's not in T. So then you're going to add this edge and its vertex, other end of its vertex, E, and W to the edge and vertex set of T, and then you're going to delete W from V. And then you're going to move on to the next value of I. It's going to output T, which is your minimum spanning tree. So we're going to take this algorithm and use it on the example we did in class last time with our other algorithm.